In this video, we're going to talk about nullity and rank. Okay, so I want to begin by defining what these are. So the nullity of a matrix A is the dimension of its null space. So in other words, how many vectors there are in a basis for the null space, because that's what dimension is. The rank of a matrix is the dimension of its column space. Okay, so let's start right away with an example now. Okay, so I have this matrix A, and I've actually gone ahead and row reduced it. And the row reduced matrix, I'm calling that B. And I want to use these to first find bases for the null space and for the column space. So that's a little bit of a review, I think, from maybe section 4.3 when we first talked about this. And then in part B, let's use those bases to find the nullity and to find the rank of our matrix. Okay, so for the null space, I definitely want to use my row reduced form. And with the row reduced form, I've gone ahead and written down the equation for each row. So remember that when I'm finding the null space, I'm solving the equation AX equals 0, and that's why I've written this equals 0 on the right-hand side of my equation here. Okay, so next what I want to do is I want to isolate the pivot variables. So in my row reduced form, there's a pivot in the first column, and there's a pivot in the third column. So we want to isolate the x1 and the x3 in these equations. So doing that, in the first equation, we'll get x1 equals 2x2 plus 4x4 minus 3x5. And in the next equation, we'll get x3 equals negative 2x4 plus 2x5. Okay. So now that we've done that, we are ready to write down x in parametric vector form. So with x, the first entry is x1, which was 2x2 plus 4x4 minus 3x5. x2 is free, so anything that's free, we leave it how it is. x3, well, we know what that equals. x3 is negative 2x4 plus 2x5. And then x4 is free, so we leave that how it is. And then x5 is free, so we leave that how it is. So the vectors in the null space are looking like this. I just need to put this in parametric vector form, so I can see what the basis vectors are going to be. So we're definitely going to get x2 times some vector. So what are the coefficients of x2 here? I see that it's a 2, it's a 1, and then 0 is all the way down. And then I have an x4 as my next free variable times its coefficients, which are 4, 0, negative 2, 1, and 0. And the next free variable is x5, so I'll have an x5 term times its coefficients, which are negative 3, 0, 2, 0, 1. Okay, so when we do this, when we find the null space of A and write our answer in this parametric vector form, these vectors that sort of come out of this process, they are always going to be a basis for the null space. Okay, so I've gone ahead and just written those down. Oh, and it looks like I made a mistake when I wrote down one of these earlier. That should have been a negative 2. But other than that, I think they're matching up. Okay, so I got my basis for my null space. For the column space, we've talked about this in a... actually, before I do column space, let's go ahead and write down the nullity. So the nullity is the dimension of the null space. How many vectors we have in this basis. And that's 3. There's 3 vectors in this basis. Remember, nullity just means, well, what's the dimension of the null space? And that's 3 because there's 3 vectors in this basis. Okay, so let's talk about column space. So we've seen before that if we want to get a basis for the column space, I have to row reduce my matrix to figure out where the pivots are. But then I go back to the original matrix and I write down the pivot columns of the original matrix. So let's go back up so we can look at our 2 matrices. So I see my pivot columns. So it's the first column, it's the third column. But I have to make sure that I go back to the original matrix and look at those columns in the original matrix. So I'm looking at the first column in the original matrix and the third column in the original matrix. So those are the pivot columns of A. And those 2 columns, they're going to be a basis for the column space. So I've gone ahead and written those 2 columns down. So remember, rank is the dimension of the column space. And dimension is how many vectors there are in the basis. And there's 2 vectors here in this basis. So that's what my rank is. My rank is 2. Okay, so next what I want to mention is a theorem that relates the nullity and the rank. So fittingly, this is called the rank-nullity theorem. So it says the following. If I let A be an M by N matrix, then the rank of A plus the dimension of the null space of A, in other words, the nullity, equals N, the number of columns. And the reason for this, we've actually talked about in a previous video, but the reason for this is the rank. What does this represent? This is the number of pivot columns, technically. But the number of pivot columns, that's just another way of saying, well, what are the number of pivots? So that's what the rank is, number of pivot columns. For the dimension of the null space, if we think back to the example that we just did, the dimension of the null space was 3. Notice that matches up with how many free variables we had. We had 3 free variables. That's always going to be the case with the nullity. So the dimension of the null space, aka the nullity, is the number of free variables. So it makes sense that if I take the number of pivot columns and I add that to the number of free variables, that what I should get is just the number of columns total. This is the number of columns total. And that's what this theorem is basically saying. Okay, so let's do some examples. So first example, let's say that my matrix A is 12 by 15, and the rank of A is 7. What is the dimension of the null space? Okay, so this is just a problem where we're going to practice using this rank-nullity theorem. So the rank-nullity theorem says, if I just abbreviate a little bit, I'm just going to write RK of A for rank of A, plus the dimension of the null space of A. Those 2 things should sum to N, the number of columns. And now let's plug in for what we know. So we know the rank is 7. Dimension of the null space we don't know. That's what we're trying to find. So 7 plus the dimension of the null space equals the number of columns, which in this case is 15. And then if I isolate here, I get that the dimension of the null space is, what is it? It's 8. So that's the dimension of my null space. So one thing I should always do is I should do a reality check. Based off of the size of my matrix, I should ask myself, is this possible? So when we said that the dimension of the null space is 8, we're saying that there are 8 free variables. 8 free variables. And in a 12 by 15 matrix, well, that's definitely possible. We could have 8 free variables. So this is absolutely our answer. So let's do another example. Okay, so here is the next example. So if my matrix A is 12 by 15 this time, is it possible for the null space of A to be 2-dimensional? So this is another way of saying this is it possible for the nullity to be 2? So let's write down the rank-nullity theorem. So the rank of A plus, let me just write it like this, the nullity of A equals N. The tip-off to me that I want to use this theorem is, the question specifically tells me something about the dimension of the null space here. It's saying, oh, could it be 2? And that's a strong tip-off to use this theorem, the rank-nullity theorem. Okay, so let's plug in for what we know. So it's asking, well, could the nullity be 2? So let's just go ahead and plug that in and see if it's possible. And then N, the number of columns, is 15. So at this point, I could isolate for the rank of A, and the rank of A is going to be 13. Okay, so now I have to ask myself, well, is this possible? Is it possible for the rank to be 13? So remember, the rank represents how many pivot columns we have, or just how many pivots we have. So this would be saying that there are, that there are 13 pivots. So is that possible in a 12 by 15 matrix? Pause the video for about 30 seconds and think about that. Is this possible is this possible? Okay, so hopefully you guys did that. Hopefully you guys thought about it for about 30 seconds. It turns out, though, that this is impossible. I can't have 13 pivots since A only has 12 rows here. Since it only has 12 rows, the most pivots we could have is 12. Okay, so that's the answer to 4. So let's do another example. So in this question, I want to know what the dimension of the subspace that's spanned by these 4 vectors is. So I want to know what the dimension of the subspace is that's spanned by these 4 vectors. So I'm talking about the span of these 4 vectors. The question that this is asking is the same as wording this in the following way. So this is the same as just asking, well, what is the dimension of the column space, because column space just means the span of the columns, if my matrix A is just the matrix where I write these vectors as the columns. So the first column is a 1, 0, 2, and then -3, -1, -1, and then 5, 2, 2, and the last column is what? 2, 1, -1. So I write those as the columns. And we know how to find the dimension of the column space. We would row reduce. And I'm just going to go ahead and tell you guys what this row reduces to. So I'm not going to go through all the steps. I'll just tell you guys what the final row reduction is. I would get 1, 0, -1, -1, 0, -1, 2, 1, and then 0, 0, 1, 0. So at this point, my matrix is in echelon form, and that's good enough to see where the pivots are. So I'm going to box the pivots. Okay, so at this point, so the dimension of the column space is how many pivots the matrix has. And this has 3. Actually, let me write it this way first. Let me just write those words first. So the dimension of the column space is the number of pivot columns, or just the number of pivots, which in this case is 3. And that's my answer, actually. When I take these 4 vectors and I look at their span, we said that was the same thing as putting them in a matrix and asking ourselves, well, what's the span of the columns? What's the column space? What's the dimension of that? And we know how to figure that out by row reduction and looking to see how many pivot columns there are, and there were 3. So just on a conceptual level, because the dimension of the subspace is 3, that means one of these vectors, at least one of them, we should be able to write as a linear combination of the others. So I just wanted to notice something. So notice that the last vector, 2, 1, -1, it turns out that is -1 times the first vector, -1 times 1, 0, 2, and then -1 times the second vector, -3, -1, -1. If we work that out, this thing on the right-hand side, it's going to equal to 2, 1, -1. So because this vector, 2, 1, -1, can be written as a linear combination of others, if I were to take that vector and sort of remove it from the set, it wouldn't change the span. And we've seen that before.